So today we're going to look at note page 161, the heating curve of a substance. So when you take a look at this heating curve, you should notice 5 individual segmented lines all connected at various points, and those points are labeled with letters A through F. When we look at the curve from point A all the way through point F, notice that point A is at the lowest temperature, point F is at the highest temperature when we compare to the y-axis. So from point A to point F, the material or the sample is absorbing heat energy quantified in joules. Therefore, it's going through an endothermic process, and each Q value would be positive. But in science, we have to be able to take a look at the data of a graph and apply the reverse idea. So starting with point F at the highest temperature, all the way back to point A at the lowest temperature, our material to move from point F to point A must be releasing heat energy quantified in joules, therefore going through an exothermic process, and the Q values would be negative. F through A, if it was plotted in that manner, would be referred to as the cooling curve of a substance. Each segment on the cooling or on this heating curve represents the stages of change that the matter undergoes during an energy transfer. So let's label what each segment represents. So segment AB represents when our substance is 100% solid. CD, our substance is now in the liquid phase, and segment EF, our substance is now in the gaseous phase. Notice that segment BC connects the solid and the liquid segments, so this represents the point of a phase change when our material changes between the solid and liquid phases. It could be solid changing to liquid or liquid back to the solid. If we follow segment BC back to the y-axis, we will notice that it strikes a particular temperature. This temperature would be known as the substance's melting point and freezing point. If you look higher on the curve, you'll notice segment DE looks pretty similar to our BC segment. It connects the all liquid segment to the all gaseous segment, therefore it represents a phase change, and this phase change is between a liquid and gas. Liquid changing the gas, gas changing back to liquid. Following segment DE back to the y-axis, and the temperature that it connects to would represent the substance's boiling point and condensing point. You need to be able to calculate the Q of each individual segment, and in order to do that successfully, you need to know which Q relationship to use. So you know that we have taken a look at 2 different Q equations. Q equation 1, Q equals mc delta T, and equation 2 is Q equals m times H. Let's do a quick reminder of what type of data or information is required if we're going to use Q equals mc delta T. Our data must show a change in temperature, and only one phase of matter is present. The sample starts as a solid, it ends as a solid. So let's take a look at the points on this graph that fits those requirements. So you notice segment A to B, it is all solid. Segment CD is all liquid, and segment EF, our sample is completely in the gaseous phase. Let's outline or point out what is going on with the molecules within each of these segments. Okay, so notice all 3 of these segments, they all have or indicate a temperature change. When the temperature changes, we now understand that we are monitoring the kinetic energy. So kinetic energy is also changing and kinetic is Greek for motion. So if the temperature changes, the kinetic energy is changing, there is a change in the molecule speed or the amount of motion. So if we have to calculate the Q for a material that's all solid, all liquid, or all gas, we would use equation 1 for each of these segments. So let's label these with the appropriate Q equation. Okay, so now let's take a look at when we should use equation 2, Q equals M times H. So Q equals M times H, we use this when there is no delta T. The temperature is not changing. The temperature might be described as being constant. Also, two phases of matter must be present. So if we take a look at our graph, we'll notice that segment BC, we see a phase change. Both solid and liquid are present. The temperature remains constant. We'll notice the similar trend at DE, a point of phase change. We have both liquid and gas present, and the temperature remains constant. What is going on with the molecules within these segments? Okay, so number one, because these two segments, BC and DE, are flat, we should understand there is no temperature change at this time. Oh, and when there's no change in temperature, that means that there's no change in the kinetic energy. It's the other characteristic of energy that is changing. So no delta T, that means we have a change in the potential energy, the amount of energy being stored in the sample. And when we change the amount of stored energy, potential energy, that means that there is a change in the intermolecular force, strength, or attractions. They either become stronger or weaker. So let's label each. So we will use equation 2 to calculate the Q for phase change segments. So let's label BC with Q equals M times H, but because this represents melting freezing point, we use H, heat of fusion. And then at segment DE for this phase change, Q equals M times H, but because it represents the boiling and condensing, another word for boiling is vaporization. So Q equals M times H of vaporization. One of the last big ideas you might come across is what is the total amount of Q or energy absorbed from point A to point F, or the total amount of energy released from point F back to point A. So this would be known as Q total. Q total represents point A to point F, or the reverse. In order to do this, you would first need to calculate the Q for each individual segment, and when that is done, then you quickly or very easily add up the 5 different Q values for the total amount of energy absorbed or released for the sample.